Recording in progress.
Okay, so let's resume our discussion. As usual, let me know if you cannot hear me or if you cannot see me or if you cannot see the slides. Um, so we'll talk now about the most common features of NoSQL systems. And as I was saying before the break, on many of these points, uh, they, depending on our perspective, we could see them positively. They may sound good or less good or problematic, depending on how we look at them. So first of all, uh, the ability of the system to horizontally scale simple operations. So now we know what horizontal scaling means and simple operations. So scale out shared nothing architectures that are capable of running on a large number of nodes. So this is, of course, a positive aspect. And then the ability to replicate and distribute data over many servers. So in general, data is duplicated, replicated, which of course has advantages. We discussed about them, but also may lead to potential problems of inconsistency. And oftentimes we will see that in NoSQL systems we depend on the application layer to make sure that such problems are avoided. Third aspect, important feature, oftentimes they provide simple query languages, simple call APIs, oftentimes less expressive than the SQL language. And in particular, we will see that oftentimes the query languages of NoSQL systems have no support for complex operations such as joins. This will be the case in the Apache Cassandra system. The rationale for that is that in a context of managing large volumes of data in a distributed setting, such complex queries are simply unfeasible, and therefore the choice is to render them impossible from the syntax level. We'll talk about this aspect in the context of Apache Cassandra later on as well. And so this can be, of course, seen as an advantage for reduced latency when we execute queries, but of course it's a disadvantage in terms of let's say expressivity of the query language. Fourth important aspect, oftentimes such systems rely on a weaker concurrency model than the ACID one. We'll see that other aspects, weak isolation and the base acronym become important instead of the ACID one. We'll clarify all this later on. Further on, such systems make efficient use of distributed indexes and main memory, which of course is leads to, let's say, significant changes in terms of system design with respect to relational database systems which have been designed roughly in the 70s, when in particular main memory was much more expensive, and that meant also basically a different role for main memory altogether, and also a different role for some other aspects, including indexing. Another important aspect, flexible schemas or schema-less data models, or so-called schema on read mechanisms, in which basically the system ingests the data, and upon reading the data, will figure out what should be the schema, what is the structure of that data, and also support for non-relational data as well. So all this, of course, are advantages, but oftentimes this also translates into certain disadvantages, such as no standardized schemas, data. So, for instance, an attribute could have a complex value. For instance, records could have heterogeneous attributes and no typing and so on, and this may lead to certain problems at the application level. And finally, oftentimes such systems, not all of them, but most of them are open source, cheap if not free, and enable fast development, especially due to important, vibrant communities of developers that are organized around them, let's say. All this is, of course, positive, but there are also downsides. Oftentimes, this may also mean that we have new and sometimes buggy systems or features of those systems. Oftentimes, we may have too many options, and it's hard to know which one to pick. There may be no guarantee for support as well. Now, in terms of examples of choices NoSQL systems may follow, for instance, with respect to transactions, some may support transactions, some may not at all, or some may look for a compromise, let's say in between, support local transactions within a single partition or shard. Um, Regarding concurrency control, some may rely on locks, the mechanisms that we have seen at work in relational database management systems. Some may rely on other mechanisms, in particular mechanisms for optimistic concurrency control, such as multi-version concurrency control. Some may rely on other ideas, for instance, pre-analyze transactions to avoid conflicts or to make sure that there are no deadlocks or no waits upon locks, or some may simply uh, disregard all concurrency control aspects from the very beginning. So no support for atomicity of updates on replicated data. Multiple users may edit replicas in parallel, and there may there may be no guarantee on which version of that data we may read. Regarding the storage aspects, some may still rely on the disk as the main storage device, and therefore caching in main memory. So the primary copy of the data on disk and the one currently in use in main memory, as in relational database systems, of course, while others may use the main memory as the main storage device and save or replicate to disk snapshots as a backup. And that has advantages, of course, in terms of performance, latency in particular, but may also lead to poor performance when the data overflows. Basically, we have more data than the available main memory storage, which is, of course, something that happens much less frequently when we rely on disk as the storage device. Other choices, for instance, for replication, we may, regarding this aspect, are all the copies, all the replicas always in sync. This may be done synchronously or asynchronously, which is faster, but may lead to problems. For instance, updates may be lost in a crash, or something in between. For instance, local copies, if we have several local copies updated synchronously and remote copies asynchronously. And in summary, we can say that NoSQL systems basically are the exponents of two main rejections, are mainly about two main, let's say, key differences with respect to relational database systems, saying no to predefined structures, predefined schemas, and declarative languages, such as SQL, which allows user to formulate complex queries over the data. It's simply oftentimes considered not agile or flexible enough to define schemas in advance, to predefine and to impose, let's say, the structure of the data before starting to ingest data. And oftentimes SQL is seen as a too complex language for let's say the actual needs in terms of API on such a system, oftentimes we'll see that even a simple so-called key value APIs and may be sufficient. For instance, a query language which supports just two operations, put by key, so put key value, or get by key. Give me the value associated to a key, or store a new key value pair. And this leads to the so-called key value stores, and we'll talk in particular about the Dynamo system, which is a precursor of the Cassandra one, and this is why we'll mention this kind of key value store system in our discussion. Sometimes the values for the data comes in different formats, for instance, semi-structured JSON data, and therefore the relational schemas are not really designed for that. And also, so second rejection, saying no to serializable transactions or relaxing transactions. It's much easier to build systems that can scale massively without this burden, the burden of supporting transactions. That enables in particular to replicate aggressively and to not use such distributed consensus protocols such as 2PC. Oops, sorry. Okay, so it's time for another quick quiz here. The two main rejections of NoSQL systems are independent, or are they independent? Can you have serializable transactions and SQL, no serializable transactions and SQL, serializable transactions, but only simple language such as put get, or no serializability, and a simple language? Of course, they are indeed independent, let's say, choices, and we could have everything in this range of possibilities here. Okay, now in order to understand some important aspects pertaining to replica consistency, and in particular, in order to understand what relaxing replica consistency may mean, we have to basically clarify what does it mean to have something different or less than strong replica consistency. So here, basically, if assuming or guaranteeing that replicas are always in sync is too much, is too costly in the system, because too slow, of course. The question is, how can we relax that? In what formal way, and what does it mean for our applications? We have to understand, of course, the risks that such relaxations to replica consistency may bring, the potential problems, basically, besides the advantages in terms of performance. And what we'll see next are a few formal definitions that can help us basically understand or interpret a consistency model. And basically, a consistency model determines, sets up, let's say, some rules for visibility and apparent order of updates. And by such rules, depending basically on which ones we have in place, we may we may have, let's say, different degrees of consistency. So already what you should note here is that what you should understand here is that replica consistency is not, let's say, a black or white feature, something that we have or we don't have. It's a spectrum of choices with different trade-offs, different advantages and disadvantages. Okay, so first of all, without protocols such as 2PC, without ways to concertate transactions across nodes, nodes that of course may hold different pieces of information, or now with replication, the same piece of information, different copies of the same piece of information. Well, without 2PC, we risk to have, first of all, per object ambiguities, especially so when we use replication. We'll see what linearizability means next. So now let's say the spectrum of potential problems or anomalies becomes wider with respect to what we discussed before, including such per object ambiguities that we didn't have before. They may come in the form of not being able to read the latest version of the data, or writers may conflict, and therefore we need conflict resolution policies and so on. And obviously we may have the anomalies or the problems that we saw before in the concurrency control section, across object, let's say ambiguities and no serializability for transactions. And typically NoSQL systems, once again, do not provide transactional guarantees for operations across objects, across different records, let's say, in a database. So without 2PC, without ways to reach a consensus for nodes participating in a transaction, we may have, let's say, all these anomalies, either anomalies for a single object or anomalies for operations across objects. And in particular, when we talk about per object ambiguities or problems, you have to understand that we talk about read and write operations over the same object. So for instance, in particular now, basically, since this is a distributed system with replication, read or write requests and read or write answers cannot and should not be seen as instantaneous. There is simply put a gap, a time gap between the request and the response. When we read, for instance, we have a request for reading a record X, the response being the value of that record. When we write, it's a request for updating with a certain value a record X, the response is an acknowledgement that the write operation has been performed. So this is important to understand in the context of our discussion. Now, basically an operation, a simple write or read operation on an object, on a record, let's say X, is a pair, a separate pair request response or request acknowledgement with some delay in between. And we need to account for that. And so per object ambiguities may come in various forms, as discussed before. With regards to that, with regards to per object ambiguities, we need basically a formal definition of replica consistency. And so this is what we'll discuss next. And so we'll talk about replica consistency with respect to updates, writes, and reads on single objects, on simple objects, let's say, on records in a database. And so ideally, when we want strong replica consistency, we want that all copies of some record X are updated together at once atomically. That basically means strong, that basically is the ideal replica consistency. In reality, of course, we cannot have that. And in reality, readers, it's enough that readers should always see, let's say, the value of X, that the values of X that they would see without concurrency. And for that, we will define on the next slide a notion of the so-called notion of linearizability. But first of all, what does it mean without concurrency? It simply means that on a specific object X, let's say all the request-response pairs are ordered, are not interleaved. So basically, a request is always followed by its response and not by another request or by another response and so on. This is, for instance, such a sequences or ordering of operations, per object operations without concurrency, in which the first request response pair appears. Then this is, let's say, ordering in time, of course, with time flowing from left to right. And so we have the first request response pair, then the fourth request response pair, then the second, and so on. And so we'll formalize what we can define formally as strong replica consistency by linearizability, and which is discussed on the next slide. And intuitively, linearizability is equivalent to serializability, but for single items, such as X, let's say, record X. And so already remember once again that what you should remember or you should take from this slide is that strong replica consistency is about the absolute ideal. All copies of an item X should be updated together at once atomically. And then the realistic ideal, which is linearizability. And so in most, let's say, definitions and descriptions of system and so on, it is said that replication protocol exhibits strong consistency if it has linearizability, if the replicated items, objects are linearizable. And once again, we'll clarify what this means on the next slide. Okay, so, regarding linearizability and serializability, once again, you should remember that they are separate, independent concepts, both important properties about interleavings of operations in databases and distributed systems, but they should not be confused. Serializability is about the isolation property of transactions, while linearizability is a recency guarantee on reads and writes for reads and writes of an item, of an individual object, for instance, a record. So a recency guarantee. It doesn't say anything about transactions. And in a system, we could have, and we could want both serializability and linearizability. Okay, so regarding this new concept, you should, first of all, you should know that it's a very important concept in distributed systems, and we could spend an entire lecture discussing linearizability. That's definitely not the goal here, but I want to give you, let's say, the main idea nevertheless. So first of all, what we called before a schedule when we discussed concurrency control in databases, well, now we'll change a bit the terminology because this comes from the distributed systems domain. We'll call it a history. So what we called before a schedule, we call it now a history. And when we talk about actions on a single object, for instance, a single record, the history is simply an ordering in time of a set of requests, request response pairs on a single object. We can see here 3 such request response pairs. So for call K, for call I, and for call J, let's say. And requests, once again, maybe for reading or for either reading or writing that specific object. And once again, when we read, the response gives the value. When we write, the response may be in the form of an acknowledgement. So in reality, so when we have such request response pairs, they are delayed. They may even be interrupted, of course. And we see here illustrated in this figure the 3 request response pairs with their corresponding delays and how therefore they are ordered in time. So here, for instance, the request K is followed by the request I, and then this one is followed by the response K, and this one is followed by the response I, and so on. And so the history illustrated here gives a certain ordering in time of the request response moments of these 3 codes. So this is what we'll call a history. Now, if we look at this sequencing in time, let's say, of request response steps, and if we ask ourselves, is this history okay? Is this history acceptable in a distributed database? the answer for that is definitely not immediate. It really depends. It depends what these calls are about, and we are not explicitating that here. We don't say if it's about reading or writing. It's about what they return, and this is also not indicated here. But what we can clarify, however, is what acceptable should mean, what okay should mean for such a history. And we'll do that in a few steps, let's say. First of all, we will define a linear history. We need the notion of a linear history. A linear history is basically one in which we have an ordering of the form call I, call J, call K, for instance. So no longer working on request response pairs, but on calls. In other words, so it's a history of atomic calls. Let's say there is no longer a delay between the request and the response. Or put otherwise, basically each request can only be followed by its response and not by some other request or not by some other response. So this is why basically we can say that it's an ordering of atomic calls instead. So history with immediate responses to requests. That's a linear history. Then we define linearizable equivalence between two histories as follows. They involve the same set of requests and responses, so they are about the same actions. And whenever the response I precedes the request J in one history, then the same holds in the other history as well. So, for instance, if we look at our example history here, of course, response I and response K, they both precede in time the request J. And so this history can only be equivalent, linearizable equivalent to other histories having this property, following the same partial ordering between calls. So in our history, once again, I and K are before J, but between them, they are not ordered, as can be seen here. But they are both before J. And finally, putting together, let's say, these two notions, linear history and linearizable equivalence, we will say that we have a linearizable history, which again has to be interpreted as a recency guarantee on reads and writes, when basically we have a history that is linearizably equivalent to a linear and meaningful history. And so here, this meaningful part basically depends on the context, depends on the application, depends what are requests about, what are responses about, and so on. So this is something that may be different from one, let's say, application to another. When it's in the context of reading or writing records, it may mean something. When it's in some other distributed computation context, it may mean something else. So meaningful basically is the application logic. If it's just about writing or reading a record, a meaningful history is simply one in which once a write completes, all read operations after that, all later reads, later by time, of course, should return the value of that write or the value of a later write. So basically, that's what we could define as a meaningful history. Whenever we read after a write, we see that write, basically. So, so this is what a linearizable history means, and this is basically what a distributed database system, and in particular a NoSQL system, should guarantee for strong consistency. That when it comes to single object operations, read-write operations, and when such basically an object may be replicated, what is executed basically is a history that is linearizably equivalent to a linear and meaningful history, one in which, once again, all reads coming after a write operation see the value of that write. So just to see an example here, this is of course, the history that we had before, and this is equivalent, of course, to a linear history such as call k. Remember, call k stands for request k, followed immediately by response k, and then call I, request I, response I, and then call j. It's also equivalent to this other linear history, I, k, and j. Okay, now once again, in order to decide whether a history is linearizable, we have to also clarify whether it is meaningful. And this is something that we did not, let's say, bring in our example. We are not saying what is each request. Is it about reading or writing something? What is each response? Is it about returning what value or what acknowledgement, and so on. So we can definitely not say if this history is linearizable, because we cannot say if it's a meaningful history. And once again, when operations are just about reading or writing a record X, meaningful means that any read operation coming after with respect to time, of course, a write operation should see the value of that write, not some older value, basically. Okay. Now, so this is about linearizability, and what you should remember basically here is that linearizability is the real world, let's say, ideal we should target if we want a system with strong consistency. However, this enforcing linearizability may be quite hard as well, may require, in particular, a coordinator or a leader, may require consensus agreement, and so on. We'll not talk further about how linearizability can be enforced, but in general, this is not something that is really adopted, let's say, for strong consistency in NoSQL systems. Instead, since NoSQL systems are oftentimes without a coordinator or without a leader, without a single point of failure, we could also say, this is the case for the Cassandra system in particular, it becomes hard to achieve linearizability. But still, if we want some form of strong consistency, then there is a weaker notion of consistency that we can settle for, and this is called a quorum consistency. So it's a weaker form of replica consistency that is often, let's say, seen as a form of strong consistency, even if this is not linearizability. And so the way to reach a consensus or a quorum or a majority, let's say, would be the following. So if we want basically to ensure that all readers see the same consistent or most recent value of a piece of information, one possible approach would be to write to all the copies, all the replicas. Whenever we write to a record, we will do it not to just one copy of that record, but to all of them. And therefore, this means that if one needs to read that record, it suffices to read just one copy and get the latest consistent value. Another approach would be to read from all copies, and if we have timestamps indicating when each copy has been modified, we can figure out which one is the latest, and therefore we can once again have access to the data consistently, have the latest value of that piece of data. And these are, let's say, extreme cases of having quorum consistency, and in between, basically, we just have to make sure that we read and write from a majority. And that will be enough to guarantee that a read operation will see the latest value on at least one of the nodes, in at least one of the copies of that replicated piece of information. So more generally, and this is illustrated here, we just need enough writing and reading nodes. So if we have, for instance, when we write to a quorum of W nodes, and when we read, so it will not be enough to just write to one copy of that piece of information, but we will write to W copies of that piece of information. And when we read as well, we read from a quorum, a read quorum of R nodes. And if we make sure that R plus W is higher than the replication degree, so the number of copies, this is what N stands for here, the replication degree of that piece of information, then we can be sure that any read operation will see the latest value of the data. And this is illustrated here. Basically, if we have a degree of replication of 5, and whenever we write something, we write to at least three copies of the data, and whenever we read from at least 3 copies of the data, then at the intersection of the nodes which have been updated and the nodes from which we read, we definitely have at least one node which holds the latest value of the data, and we see it when we read that piece of data. So this is what quorum consistency stands for, and we will see later on that is how, for instance, the Cassandra system allows us to go, let's say, to get as close as possible to this notion of strong consistency. Okay, now this is a slide basically illustrating that quorum consistency is not linearizability. We'll not discuss it further here, but you can have a look at this later on. It's about operations that start that are read or write operations that are done on an object which is replicated with a degree of replication of 3, and there are delays, let's say, in between the request and the response for each of them. Okay, so conversely, let's say giving up consistency. So if we don't want strong consistency, and that may mean definitely not having linearizability or even not having quorum consistency, giving up consistency leads to so-called weak consistency, which roughly means that a read operation does not necessarily guarantee the return of the latest value that has been written on that object. And it may come as a surprise, but often in systems supporting major web applications such as Amazon, Facebook, and so on, this may be considered fine, unacceptable loss, let's say, in order to gain in efficiency, in latency in particular, and availability. Let's say the capacity of the system to always answer queries, always answers with something, instead of answering that the system is not available. So simply put, weak consistency leads to a highly scalable system because there is no need to involve more than one replica or more than one node into a client request. That's a simple explanation for this trade-off consistency scalability. And if we, let's say, if we wonder what weak consistency may mean, what is usually offered or usually, let's say, marketed in many NoSQL databases, including the Apache Cassandra system, is a so-called eventual consistency. Simply put, basically, so why do we have eventual consistency? Simply because weak consistency sounds too negative, let's say, and therefore a different term, eventual, is used mainly, let's say, for marketing purposes. Eventual consistency indicates that replicas, basically copies of the same piece of information, the same record, tend to converge to the same data state. So basically, if no new updates are made to that object, eventually all accesses will return the last updated value. And so basically, if we stop writing to the database and sorry, wait for some unspecified length of time, eventually all read requests will return the same value. So in a way, we could say that eventual consistency strengthens a bit weak consistency, because weak consistency can mean anything. Simply saying that replicas tend to converge to the same data state if the system is idle. So this may sound better overall than weak, but in practice it may mean the same kind of problems, the same uh, uh, unpleasant situations that we can have as with no consistency at all. For instance, reads may get non-deterministic versions based on what replica we use. Replica values may diverge permanently. You may not be able to read your own writes, especially not immediately after your own writes, and writes may be applied out of order with reality and so on. And so with this assumption, this decision, let's say, to give up strong consistency at the system level, obviously this puts, let's say, the burden on the programmers and on the application itself. The burden now shifts to the application level, and so one must make sure basically that uh, uh, the application is correct, there are no race condition. What happens in the case of failures? Will it remain correct even if, well, some other developer, for instance, takes over the application? How does it interact with other applications and so on? So all this basically, in many scenarios, renders uh, the the job of the developer and the challenges at the application level very, very important. So and obviously when confronted with such problems, we may want to go back to the transaction model of relational database management systems. Okay, now what we will discuss next is a way of charting, in a way, the different NoSQL systems along three main features that they may or may not have. And to do that, we need to understand, first of all, the so-called CAP theorem, which is, in a way, an impossibility postulate. So the three features along which we'll want to describe NoSQL systems are availability, consistency, and partition tolerance. These are, let's say, three basic requirements for distributed systems, and we'll clarify each of them next. So basically, this postulate says that we cannot, with respect to, so basically network partitions are major failures, which may cut, for instance, in half a distributed system, separating the nodes from one half from the nodes of the other half. This is what partition failure means. And this postulate says that with network partitions, you cannot have both 100% accuracy or consistency and 100% node availability. So it's impossible basically to fulfill all three features, to have all three features in the same system. So consistency, once again, means that all nodes see the same data at the same time. Availability, every request receives a response, so the system is always available. And partition tolerance, basically we have a system that continues to work, is robust even when confronted to major failures, and in particular major networking failures that may, for instance, split the system in half, for instance. So nothing short of a complete network failure and the system keeps functioning. And basically this theorem says that it's impossible to have with in the presence of network partitions, so when network partitions are possible, so when we have a largely distributed system, it's impossible to have at the same time consistency and availability. So basically, so the C in the CAP theorem is about once a writer has written an object, does the system guarantee that all readers will see that value? So this should be already clear. The availability feature is basically about is the system available regardless of the failures it may encounter. And for instance, when it's about relational database management systems, we say that they are highly available. We often times use this 5 nines reference. Such systems are 99.999 of the time available. That may mean, for instance, in a year they may be down a few minutes or so. Can we have something like that in a NoSQL system? So we want a system that basically is resilient in the face of all failures, including major network failures, major, let's say, partition failures in the system. And the P basically represents the fact that the system can continue to operate in the presence of large failures, network partitions. And so the theorem says that you cannot have, you can have at most 2 of these properties in any shared data system. And so basically with network partitions, with the possibility of having network partitions, once again, you cannot have both 100% accuracy, so consistency, and 100% node availability. And that also immediately means that basically when designing a NoSQL system, we have to decide what to give up, what to drop. So we might exclude from the picture the possibility, the risk of having major failures, partitions. So we drop partition tolerance, and that obviously can only mean we don't distribute, we don't decentralize, but that of course may lead to, that means we cannot have a scalable system. We may drop availability, and that may mean when there are major problems, when there are partitions in the system, when there are major failures, there may be moments, situations in which we cannot answer queries. The system is not available. The system has to wait for all the nodes to get back in line, to synchronize before allowing usage for some part of the data. And then we may choose to drop consistency, and we may choose to embrace basically weak or eventual consistency, which seems once again acceptable in many web applications. So basically this, by choosing one of these options, basically this leads to different designs of NoSQL systems. So basically as a summary for this way of charting NoSQL systems, we therefore can have CA system. So we drop the P, we drop the possibility of having network partitions, but that means centralized or tightly connected, let's say, single site clusters, where all nodes are always in contact with one another, and basically partitions cannot happen, or if they happen, basically it means that everybody is blocked. So it's as if the whole system is down. CP, so we drop availability. Some data at some situations when we have a major failure or a partition, some data may not be accessible, but the rest of the data remains accessible and accurate, consistent. And we have AP systems where we drop the C, we give up strong consistency, and so the system is available even in the case of major failures of network partitions, but some of the data that may be returned in such situations may be inaccurate. So, and what is important to understand here is that the A and C are asymmetric in the sense that when we give up the consistency feature, it's at all times, not only for situations when we have a network partition. Basically, at all times, regardless of whether we may have a major failure or not, the system is available, will always answer with something, but that data may not always be the most accurate one. And when we give up availability, this is only when for situations when the network is partitioned, when we have major failures. And so this is illustrated here with a few systems such as for instance, MongoDB, the most popular document-oriented system, which is a CP system. Cassandra and DynamoDB, for instance, are AP systems. So they give up on consistency. We'll see in the context of Cassandra what this may mean. While relational database systems are here, basically they exclude from the picture the possibility of having major failures partitions. Okay, and as a conclusion, let's say to this part of our discussion, we will replace the good old ACID mantra that we used until now with a new acronym, the BASE acronym, which stands for several things. It's about systems that are basically available. So the system guarantees availability in the terms of the CAP theorem. So for instance, if there are major failures partitions, the system may not be available. Soft state, this means that the state of the system may change over time on its own, even without input, even without actions from users, requests for writing or reading and so on. And this may be because of the eventual consistency model, which means that replicas should converge at some point when the system basically is idle. This is what soft state is about. And the eventual consistency, the system will become consistent over time, assuming that that the system is idle. There are no longer, let's say, requests for reading, writing that piece of information. And when this is the case, eventually the replicas will converge and have the same latest consistent value. Okay, now as a final note, many systems basically market themselves as eventually consistent because this is something that is quite fashionable, but in fact, they may have significant differences in terms of what they give up. But some of them may provide some mechanisms for some degree of consistency or for some degree of concurrency control. So it's really important to go beyond the usual fashionable keywords, let's say, such as eventual consistency, in order to understand in detail, in more detail, what the system you may want to use does guarantee in terms of consistency and does in terms of concurrency control as well. Okay, so now that we have finished, let's say, the generic discussion on NoSQL systems, and we'll now talk about examples of such systems, and in particular, we'll focus on the Cassandra system for which the third practical assignment is about. So in terms of data such systems may handle, there is another classification. Graph databases, so they handle graph data. Document databases, they handle usually semi-structured JSON data. Key value stores, they handle key value pairs data, and column family, which basically is a generalization, let's say, of key value stores. And so let's start our discussion with key value stores, and with the DynamoDB system. We'll briefly discuss it because many of the ideas from the system will then be found as well in the Cassandra system. So here, the bottom line, the initial, let's say, motivation is that we want a scalable, simple model that allows us to distribute a large collection of key value pairs. This, of course, is built on a technology that you know and use all the time. So basically, the hash map in Java, for instance, is a key value data structure. It enables basically two simple operations: put key value and get a value by key. And basically, if we want to use that, of course, in a main memory setting, we could use any main memory key value structure. But if we want to use that in a database setting, we need a persistent key value collection, of course. And we could argue, is this a file system or a database? What may be the advantages, the disadvantages of having such oversimplified or simplified data formats? But it's an important scenario in the NoSQL world with, let's say, quite important examples of NoSQL of key value stores such as DynamoDB, Redis, and many others. It's in fact I would say the category of NoSQL systems which has the largest number of exponents, the largest number of systems. And so one of the initial and most popular examples of key value stores is the DynamoDB system, which comes from Amazon. It's also one of the few NoSQL systems which is not free, open source, and so on. So it's can be seen, let's say, as a highly available key value store. And it pioneered many important concepts in the NoSQL world, such as eventual consistency, so giving up consistency for higher availability and scalability. The query model is, which is just put and get by key, is motivated by the fact that in the applications there was no need for relational schema, and therefore a simple read-write based on a key was enough. They introduced eventual consistency in exchange for higher availability, and they used replication, and all this was done also in order to meet certain service level, certain levels of service agreement, let's say, on latency and throughput. So for the clients using the system, they were guaranteeing that they will always respond with a certain maximal latency within 300 milliseconds, for instance, for most of the requests, for 99.9% of the requests. So this was one of the key features of the system, I would say. It was based on a decentralized architecture and no single point of failure. And we'll clarify next what is this decentralized architecture. So the main features of a typical, it applies to DynamoDB, but not only, of a typical key value store would be the following. So a very simple API, so the possibility to fetch values associated to a key and to put values associated to keys. Sometimes we may have more complex operations, multi-get, multi-put, or range queries. Oftentimes the consistency model is atomic put operations. So this will be done basically all or nothing, but besides that, not much basically. And in terms of implementation, in order to understand, first of all, how Dynamo basically followed certain options and became a distributed system, and this will also apply to Cassandra as well. Let's do a little exercise of design, basically, and let's say we want to design a system for managing a very large hash table, a very large collection of key value pairs. The option one basically would be to just use a big in-memory hash table, but obviously this is not persistent and we may not have enough main memory. The second option would be to basically use a traditional relational database system, which and the table basically with just two columns, key and value. The problem with that is, well, that will probably not scale. It will not be feasible if the data basically does not fit in one machine, and we are also facing situations in which the volume of data can evolve rather rapidly. The workload as well can evolve rather rapidly. So in order to solve the scalability problem, the obvious option would be to partition the key space across multiple machines. For instance, we could use hash partitioning. We could use n machines and basically store each key at a predefined machine, for instance, by applying this hash function that basically has as output 1 to n, let's say, or 0 to n minus 1. Now, the issue with that, of course, is we need to know which, when we query such data, we need to know which physical machine to contact. If we have the key, of course, we can apply the same hash function and that would work. But more important, other limitations, major issues would be that what can be done if we add a new machine to the cluster. If we figure out that n is no longer enough, we need maybe 2 times n. So one or several machines have to be added in the cluster. Obviously, we need to recompute entirely the hash table and to repartition the data according to a new hash table, for instance, mod 2n instead of mod n, or mod n plus 1 instead of mod n. And that would obviously not be feasible if we already have a lot of data already distributed across many nodes. What happens if a machine fails for availability, for accessing the data that machine holds? What if we also want to replicate? And remember, we have good reasons for replication as well. So the solution to all these issues is to hash the machine, to hash the keys as we did before, to partition the data, but also to hash the machines. And we'll immediately see what this means. And this bears the name of distributed hash tables, DHTs. And so here's an explanation for DHTs, an illustration for that. So assume that the hash output domain is a circular one. For instance, 0 to 2 at the power of n, so a very large number. And the 0 and this maximal value, 2 at the power of n, are consecutive, basically. So 0 is here at the very right base, let's say, of this domain limit, and 2 at the power of n is right before it is here. So this is why we say that we have a circular domain of values, and therefore, for instance, the dots that we see here are the data hashed into this circular domain. And so we see here the hashed data points, and also we will hash the machines. So for instance, we'll apply the same hash function to the name or the identifier of each of the machines, of each of the nodes participating in our system. And the assumption then will be that each machine will be responsible for holding, for managing the data from the sector preceding it. Sector, of course, in this circular domain. So basically, this will be the way by which we decide and we know which machine is responsible for which part of the database. Now, so in order to figure out which machine holds a certain key, of course, as a user, for instance, sending a read request, we need to basically start somewhere. For instance, we may have as a starting point or an entry point in the system any of the nodes, not necessarily the one holding the data we want. And therefore, we need a way to jump from one node to another until we reach the node having the data we want. And for that, basically, we may have next and predecessor and successor pointers, and that allows us to basically jump from one machine to the next or to the previous. And so in this way, we can start our lookup, for instance, anywhere at any node we may know or we may have as close by, let's say, and then follow next or previous pointers to land on the right part of the circular domain where that piece of information is. But obviously, following next or previous pointers may be slow, and so we can do better. Basically, we may visit all the nodes if we are unlucky in the system, and there may be many of them. We can do better by, for instance, assuming that nodes have pointers to nodes that are farther away. For instance, nodes may have pointers to the node at distance 2, then the node at distance 4, then the node at distance 8, and so on. For instance, pointers to hops, which are powers of 2. And that allows, of course, a much faster lookup logarithm in the number of nodes in the system. Okay, so this is about knowing, first of all, which node holds the piece of data we are looking for, and accessing that node, getting to that node in order to perform the read to see the value we are looking for. Now, there is even a simpler solution with respect to hops in this way. We may even say that we have at each node, we have a so-called registry that allows each node to know about all the other nodes in the system, and therefore just a one hop jump, let's say, would allow us to reach the right node holding the data we want. Now, remember, there were other issues we wanted to deal with. What if a new node joins? We don't want to re-partition everything. We don't want to reorganize the data because we just change the system from n nodes to n plus 1 or from n to 2n, for instance. So what if this node here just joins? Well, the same idea remains. That node will be available, will be responsible for the sector of data, the sector of the circular domain preceding it until the node that comes before that, the new one. So basically, when a new node arrives, basically sector of the circular domain will be split basically into, as illustrated here. We may have to rebuild some predecessor, successor fingers tables, but that is all that is required here. No moving of data, moving data around is required. There is a paper that lays, let's say, the main principle of this distributed hash tables. It's called CORD, a scalable peer-to-peer lookup service for internet applications, if you want to learn more about this approach. Now, what if a machine fails? How do we prepare for that? By replication, of course. And the question is, how do we replicate? Well, for instance, we may decide that whatever a node holds as in terms of data will also be replicated at the previous node and at the successor node. For instance, whatever this node holds will also be replicated at the previous and successor. For instance, n equals 3 here, we have a degree of replication of 3. And so if this node fails, basically, we got it covered by its neighboring nodes. Okay, how do we, how do we actually replicate? So once again, this can follow various options. For instance, we may choose to replicate at the previous and next node, or we may choose to replicate at the next and the one after. So at hop 1 or and at hop 2 with respect to a specific node. There are other, let's say, adjustments that can be made or refinements that can be made here. We may not directly hash the actual machines, the actual, let's say, identifiers of nodes. Instead, a node may represent a larger number of virtual nodes, and then those will be mapped to physical servers, physical nodes, and that allows for a better load redistribution in the event of failures. And when new servers join, basically it allows also to better share the load from other servers. So basically, each physical node will be represented in the system by a certain number of virtual nodes. Okay, so regarding now another kind of system, the so-called family of wide column stores. we'll talk next about one exponent of this family, which is the HBase or big table system, also because its main principles are found in the Apache Cassandra system. And so this is called wide column, or sometimes it's called column family stores. And we will use HBase as a main example. So basically, HBase stands for Hadoop base. Now, first of all, what are column stores? This is a new concept here. You may have heard about it. It's simply about the physical organization approach that we follow when we store data. We might want to do it by rows, so basically order the data by as a collection of row ID, for instance, and then the record itself. Or we may want to organize the data at the physical level by column. And so this is illustrated here. This would be a row store in which we see one record after the other. And this would be a column store in which we see one column after the other instead. So basically this means that instead of key record pairs, we store key, or let's say row ID attribute values instead, so columns. And so we'll now distinguish, let's say, between row stores, the classical systems and physical organization we had until now, let's say, and column stores in which at the physical level, basically the data is organized column by column instead of row by row. And why would we want to do that, first of all? Well, this may have advantages. Row stores make it easy to modify a record. We might, but because we will have a direct way of reaching, let's say, the physical address where that record is, but we may read unnecessary data when processing. With column stores, reading operations are much more efficient. We only read the necessary data that is required for that processing, while record writes basically may require multiple accesses, because for a single record, basically we have to write different attributes in different places. So basically column stores are optimized for reading and in particular for analytical processing, while row stores are optimized for read-write operations for a few records that touch a few records, let's say. So basically what you should also remember here, that the logical schema of the data remains the same. For instance, if we talk about relation with attributes ABC, that remains the same. It's just the physical storage that is different, basically the physical layout of the data by column or by row. So regardless of the row column physical organization, basically the logical view of the data is the same. We talk about a relation with attributes ABC, for instance. Okay, end of this parenthesis on column stores. Wide column stores or column family stores basically take this idea of column-oriented organization a bit further, accommodating not just one attribute per row ID, let's say per key, but multiple attributes or multiple columns per key in a distributed data structure. So now columns will be grouped into so-called column families or super columns, and this is what will be then organized in the database. And so oftentimes the key may be a combination of table ID, row ID, and then column family ID, column, and even timestamps. So we may keep different versions of the same data. And so all data accesses will be done by such a key. The value we may get corresponding to a key may be even an uninterpreted array of bytes. And exponents of this family are the Google Bigtable and its open source free version, which is Hadoop based, and then the Cassandra system that let's say reuses some of the ideas coming from Bigtable and HBase. Okay, regarding HBase, we're not going to many details, but you should know it's one of the most popular systems within this category. It works on the Hadoop file system that we'll also mention in next week's discussion on big data systems. And basically, it enables to manage a sparse, distributed, persistent, multi-dimensional sorted map. So a hash map, basically, in which uh, uh, we have the data indexed by a certain, let's say, multi-dimensional key, for instance, row, family, column key, timestamp, and then the value. And this is an illustration coming from the use of Hadoop or big table, so HBase or big table, in the scenario of web crawling for and web indexing for search. And how, so here basically the values will be actual web pages, and then we will um, uh, index that by a key that enables us to get a certain version of a web page, for instance, for a specific timestamp. Okay, regarding HBase, some of its main benefits are it enables distributed storage or on commodity hardware, and basically it enables to distribute data that on horizontally on thousands of commodity servers and deal with large volumes of data, petabytes of data. Um, and so it's a very efficient distributed storage for relying on commodity hardware. Um, it's highly scalable and provides strong consistency. So it uh, it makes sure that basically the data we are accessing is always consistent, and it scales basically linearly. Remember the scaling curves that we saw before, and automatically when new nodes must be added in the system. Um, there are also major limitations of HBase. Not everything is perfect here. Um, there are no other ways of indexing the data. There is just one primary index by the row key, let's say. The API, the query language is very simple, no join operations, only lookups by key, basically, or full table scans, or sometimes range scans. Um, all the aspects such as partitioning are automatic, so not under control of the user. Um, there is limited transaction support. Data is unstructured and untyped. So basically we get just blobs, arrays of bytes as a value for a specific key, and there is no query language. So basically the access is, we have to write little programs, for instance, in Java or Ruby in order to access the data. Use cases for HBase, for instance, the web crawl and web indexing activities, or Google Earth or Google Analytics, sessionization, so breaking up, for instance, web accessing information into sessions, or analytics, for instance, for advertising, for web advertising. And if we were to just looking, of course, at the surface, and if we want to compare HBase with relational database management systems, such a system is ideal for a variety of use cases within, let's say, platforms such as Google. And so it's optimized for read or write operations with scalability, but it's not good for transactional applications or relational analytics, so applications that need full table scans, data to be aggregated, analyzed across rows, and so on. Okay, now we are reaching the Cassandra chapter, but unfortunately we are out of time. So we will continue our discussion about Cassandra. We'll finalize the discussion on NoSQL systems and talk about Cassandra next week, of course, before moving the discussion to big data systems. So you can, you can have a look over this set of slides before next week's class in order to have already maybe an initial understanding of this system before the discussion in class. And the practical assignment with Cassandra will also be released next week, so within so next Wednesday, immediately after our lecture, the final lecture, of course, of this class. So this is basically these are the remaining steps in our class. So next week we will finalize the discussion on NoSQL systems with the Cassandra section, and the practical assignment 3 will also be released. Then we'll talk about big data systems and the practical assignment on with the Cloudera the Cloudera quicksort the Cloudera, sorry, well, the Cloudera Docker system will also be released, and within that system, basically, you will have at your disposal not just one but several big data systems. So this is what you will use in the fourth and final practical assignment on big data systems. Okay, so we'll stop here for today. As usual, at 6, I will move to, I will be in the other Zoom meeting for the office hours, and you can enter this meeting one by one to ask your questions. Remember also that the practical assignment 2 is due by the end of the week. So the practical assignment on concurrency control with Oracle.